In today's presentation, we're going to look at something called oxidation number. It's a very useful concept that we can use to really quickly find out if something has been oxidized or reduced. So it's not always apparent by simply looking at the change these substances undergone. So basically, it works like this. For some reactions, particularly those that involve covalent molecular substances or even covalent network substances, it's difficult to determine which reaction has lost or gained electrons. When you look at something like magnesium going to magnesium ions, so Mg going to Mg2+, you can really easily see that the substance has gone from its neutral state to a +2 cation. So you can see that, or to go that way, it must have lost 2 electrons. So it's really obvious to say, hey, well, that's lost electrons, that's been oxidized. Also equally easy to see something like chlorine in its neutral state, CO2 molecule, has gone to 2 chloride ions. Each ion's gained 1 electron, so it's gone from 7 in a valence shell to a full valence shell per atom. So when that happens, it's really easy to say it's gained electrons, it's been reduced. But for other things, it's not quite so easy to see. So for example, if you look at the combustion reaction for methane, we've talked about the fact earlier on that it is a redox reaction. The carbon has been oxidized, it forms its oxide CO2, but there's no ions involved. And without using that old traditional method of defining redox, it'd be hard to say what's undergone what process. But we don't want to use that old historical method. We want to use something with a bit more rigor to it. And also, knowing about oxidation numbers is really helpful in exams. Often you'll be given 4 multiple choice questions or 4 options for a multiple choice question, and they'll say, which of the following reactions represents a redox reaction? And you'll be given things like, for example, HCl plus NaOH goes to NaCl plus H2O. Now, that's not a redox reaction at all. Okay, that's an acid-base reaction, it's a proton transfer, but how could you tell really quickly from a list of reactions which one's which? Well, you could go and try and write half equations, which we'll practice doing later on, but there's a much easier way, and that's where this thing called oxidation number. So to allow us to be able to predict whether something has been oxidized or reduced, and actually be able to very confidently say this has been oxidized, this has been reduced, then we've got a set of rules that we've designed to calculate something called an oxidation number. Now, an oxidation number is something you haven't come across before. You might have seen it on some of the older periodic tables we've got on the wall. You can see above the elemental symbol, there's often some plus and minus numbers. They're actually the oxidation numbers. Sometimes they are linked to the ions that we know really well. So you think, oh yeah, I already know this, but it can be a bit more complicated than that. Some substances only have 1 oxidation state or 1 oxidation number, which is really helpful. So like group 1 elements, for example, only have 1, they're +1, that's it. But some of the transition metals, something like manganese, has many oxidation states depending on what compound it's in, so it can get a bit more complex for substances, especially in the middle of the periodic table. They're the ones you really got to worry about. So the concept of oxidation number is based on the assignment of something that's equivalent to ionic charge on every atom within the chemical formula of a substance. But it's really important that it's the equivalent of an ionic charge. It's not an ionic charge. So when we look at methane, for example, we'll look at methane and I'll tell you that the charge of the carbon, or the oxidation number of the carbon in methane, is -4, and that the hydrogens are +1. But it's not ionic at all. It's still covalent molecular. There's no charged particles within that. I'm talking about an oxidation number as an arbitrary number been assigned to say what its state is at that time. When the methane is burnt, it goes from -4 in the methane state, but when it's in CO2, it goes to +4. And because the oxidation number has been increased, we say that it's been oxidized. How we get to those numbers is what this lesson is all about. So be careful with that concept about these oxidation numbers. They're not ions. So as it says there, it contradicts the concept of covalent bonding. This is a tool that you can use to identify redox reactions. It's not an actual thing that's happening within the substance. Okay, so because it's a tool, it's got some very simple rules, and this is one of the times when you have to learn some rules. I don't like to say memorization in Year 12 Chem. We try to stay away from that concept, but there are a few rules that you have to learn to get this mastered. This is the easiest one. For elements, they're in their neutral state. if the element is in its neutral state, its oxidation number is 0. So magnesium, aluminium, zinc, all metals, in their natural state, neutral state, oxidation number is 0. Oxygen, O2, that's the neutral atomic state. Well, it's not an atomic state, of course, it's a molecule, but it's the natural elemental state, I should say, 0. Phosphorus exists in P4, sulfur S8, so it's 0 in the elemental state. So that's the first rule that we have to learn. It's an easy one. For other substances, for monatomic ions, so a monatomic ion is a single atom ion. It's the same as the charge. So again, you don't have to learn anything new, you already know these. So for example, sodium, +1, oxidation number is +1. And we always put +1. We don't say it's just 1, it's +1. The sign is important. For chromium, 3+, it's +3. P3-, -3. Bromide, -1. So ions are really easy for monatomic substances. So we've got elements 0, monatomic atom ions are the same as the charge of the ion. This is the most important. Well, there are two really important rules. One is the oxygen and one is the hydrogen. Oxygen in compounds is -2. So oxygen in compounds is -2. So for example, in CO2, the oxygen is -2. In Na2SO4, it's also -2. In CaCO3, it's -2. In CaO, it's -2. Whatever the compound is like that, it's -2. So that's an easy one to remember. Of course, there are always exceptions to things. When it's a peroxide, so for example, when it's in the O2 state, it's -1. There aren't many of those. F2O, for example, that's when it's that's when it's +2. Na2O2, sodium peroxide, H2O2, in those two examples, it's -1. F2O is when it's an oxidation number of +2. That's a unique one. So there's probably 3 that you're going to come across. Sodium peroxide, hydrogen peroxide, and F2O. So those ones just be careful of, but oxygen and everything else, -2. Hydrogen. Hydrogen's another important one. It's +1 in pretty much everything. So hydrogen in bicarbonate, hydrogen in sulfuric acid, hydrogen in hydrochloric acid. So it's the same as its iron, right? It's iron. We know there's not really a H+ ion, but same as its iron. Except if it's a metal hydride, and there aren't many of those. That's where you put a hydrogen and a group 1 metal. You've probably seen this on the back of batteries, lithium hydride, things like that, LiH. Then it's -1, but they're only for the group 1 elements with a hydrogen, so they're metal hydrides. So watch out for those ones. But hydrogen's -1. So the two most important rules: oxygen -2, hydrogen +1. Okay, so let's have a look at the more important ones, or the more tricky things. When you have a molecule, CO2, SO2, H2O2, CH3C-, whatever the molecule is, all of the oxidation numbers of all the individual atoms within that molecule must equal 0. So for example, CO2, the carbon and the 2 oxygens, the sum of their oxidation numbers equals 0 because it's a neutral molecule. Okay? No leftover bits. So for example, and we talked about this a few minutes ago, what is the oxidation number of carbon in carbon dioxide? So this is how we work it out. Now you don't have to write these equations out, you can do it in your head. But as you're learning, you might feel that you need to write this little bit of mathematical workings out to help you out. But this is what you look at. So say, right, the oxidation number of CO2 in its entirety must be 0, which is equal to the oxidation number of carbon plus 2 oxygen atoms. 1 carbon plus 2 oxygens must equal 0 in terms of the oxidation numbers. If we know that the oxidation number of oxygen in molecules is -2, because that's one of the rules we learned, we say it's the oxidation number of CO is carbon plus 2 times -2. 2 times -2 is -4. So therefore, if we rearrange that equation, and we know that CO2 is 0, and we know that oxygen is -2, carbon must be +4 by rearranging that equation. So in CO2, carbon has an oxidation of +4. But what about in carbon monoxide? Would it still be +4 or would it be something else? Well, oxidation number of carbon monoxide, a molecule is still 0. It's made up of 1 carbon and 1 oxygen. Oxygen is still -2. So what do you get? How do you get CO to be 0 if it's carbon plus -2? Carbon must be +2 for that one. So far we know that elements are 0. Monatomic ions are the same as their charge. Sodium is +1, magnesium is +2, aluminium is +3, chloride is -1, sulfide is -2. So they're the same. Molecules are 0 because they're neutral and all the bits add up to 0. Remembering that oxygen is -2 with those few exceptions and hydrogen is +1 with those few exceptions. What's left? Well, polyatomic ions are left. Things like carbonate, phosphate, sulfate, nitrate, nitrite, those sorts of things. So with polyatomics, the sum of all the oxidation numbers all add up to equal the charge. Okay, so for example, for nitrate, 1 nitrogen plus 3 oxygens equals -1. They all must add to -1. So this is not too difficult. Things like manganese is +2 as an ion, but permanganate, MnO4- would be -1. But MnO2, neutral, would be 0. So we add them all up to different things. So what about nitrate? What is the oxidation number of the nitrogen in nitrate? We know oxygen must be -2. That's one of our rules. So the whole thing must equal -1. That means it's 1 nitrogen and 3 oxygens. So 3 times -2 is -6, obviously. -6 to equal 0. So what's the -1 rather? What's the nitrogen got to be? It's going to be +5 because +5 take 6 is -1. That's how we get that one. What about in carbon? We looked at carbon before. So far in this video I've talked about carbon being -4 in methane. It's +4 in CO2. It's +2 in carbon monoxide. What about in carbonate? CaCO3. CO3, sorry. CO3 2- has a charge of -2, right? So the whole thing must be -2. 1 carbon plus 3 oxygens equals -2. Oxygen is -2. So you've got this equation here. So a bit of simple maths in your head. 3 times -2, -6. The net has to be -2. What's the magic number I'm looking for? Carbon must be +4. Same as it was in the CO2. A particular atom often exhibits different oxidation states or exists in different oxidation states in different compounds. So as well as having oxidation state 0 in its free element, chlorine has 5 other different oxidation numbers as shown in some periodic tables. That's a little number above the elemental symbol. Manganese is another one. Chromium has a lot of oxidation states as well. So there are certain ones. The transition metals are more prone to it than others, but don't just expect that because you got +2 for an oxidation state in another example, it's going to be that again. Hydrogen and oxygen have oxidation numbers of +1 and -2, except for those exceptions that we've had before. Now, one of the most important things is not only are you able just to look at the oxidation number within a substance, but also can you calculate or can you determine what the change was? And that's the important thing in our multiple choice questions. Let's just have a quick look at the summary though. Alright, overall oxidation number of an element or molecule is 0, which is the sum of their component parts. A monatomic ion is the same as the charge. A polyatomic ion is all the components must equal the charge of the actual ion. Where oxidation number of oxygen is -2 in all cases except in the peroxides where it's -1, and hydrogen is +1 except in the metal hydrides where it's -1. If you have a ionic material, often this causes problems in some of our sets that we do, split it into its ions first will help you. So for example, if I gave you potassium permanganate, KMnO4 is the molecular ionic formula unit for that, KMnO4. If you tried to do that like that, you'd look at it and go, well, I know oxygen is -2, and -2 times 4 is -8, but what about the potassium and the manganese? Well, first of all, split it. If it's ionic, split it into its 2 bits. If you did that, you go K+, well that's +1, sort that. MnO4-, that's that one. Oxygen times 4 -8 must be -1, manganese is +7. So if you can split something into ions, do so first, then look at the oxidation numbers after that. Now what we want to look at is this change in number, as I said before. If the oxidation number has increased from one species to the next species in an equation, if it's gone from 0 to +2, like when you go manganese to manganese 2 ions, it's been oxidized. So if the number goes up, then what we've got is we've got a oxidation. If the number goes down, so for example in chlorine, it's 0, going down to chloride, -1, it's gained electrons, it's been reduced. So if the number goes down, we're looking at a reduction. And you need to look at each equation individually to see what happens. Okay, so that's the basics about oxidation number. There's lots of practice questions that you can work through. I suggest you have a go of those, but it's a really useful and quick tool to quickly figure out whether something has been oxidized or reduced, and that can be really handy when we're in an exam situation and we're trying to save time. Alright, and we'll see you next time.